Hello everyone, welcome back to the course. Now we will see a video. The other people explained it, the handwrite digital recognition, and we will see the video from YouTube. And here we are.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation, and the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment, and 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve.
Okay, we stop here, and we can see the from the video explaining how the AI to recognize the handwritten digital number. And the left part is about the mathematics, like how this sigma does, or how many sigma function we can do and change the value from the weight or the other parameters. So if you have an interest in, you can see the left part by yourself. And let me back to the slides. Now we know the idea of AI and deep learning, and then we will see some real algorithms. And for example, and you can use this algorithm to do the image recognition, like this one, or you can do the spam filtering. You can push it in your mail server and to check the spam, like the keyword here, or you can see the newspaper and extract the keyword you want. For example, like the sport, finance, and local news, and you can collect it automatically and summarize them by AI. And then that is very important in the neural network. And there are two major neural networks here. One is called a convolutional neural network, and the other is called recurrent neural network. And maybe you have heard some neural network, and they are the part of our enhanced CNN or RNN. So we introduce the major and the basic neural network here. Here we first introduce CNN, how CNN works, and then we introduce how RNN works. And in fact, CNN is measured to handle the space part, like the figure or like a space and the object. And RNN is responsible for times, like the sequence and the time and the sequence. Okay, we see the CNN first, and it is usually what used in the image processing. For example, you see this figure as same as the video show. If you have a cat, and then it will extract its feature in each layer, and then you will get know what kind of figure or photo it is, and then it can output it is a cat or a dog. Okay? And why CNN can do this. And you remember that in our slide before, we have many layers here, and the figure represents as a pixel to our input, and then the most basic classifier is here, and we can get the sum like the color or the background or something, and then use the first layer to build a classifier, and the second use the detail classifier, and so on. And then you will distinguish what is it in the image. Okay. If we see the steps in the whole CNN, we will see that the figure, and then it will go to the convolution, and then it will do the mask pooling, and then this is one term, and then it will do a next term again, like convolution mask pool and the convolution mask pool, and this can be repeated many times. And then after this, the parameter or the elements will go to the flatten, and then go to the full connect network and do a lot of feature extraction and the compression, and then we will get the answer. Okay. And here we see the video about the CNN operation in detail, and we will see how can the CNN detail with the figure and output the answer. Maybe I would say possible answer.
What is a convolutional neural network? Well, let's start with the basics. A convolutional neural network is a type of neural network that is most often applied to image processing problems. You've probably seen them in action anywhere a computer is identifying objects in an image. But you can also use convolutional neural networks in natural language processing projects too. The fact that they are useful for these fast-growing areas is one of the main reasons they're so important in deep learning and artificial intelligence today. Once you understand how a convolutional neural network works and what makes it unique from other neural networks, you can see why they're so effective for processing and classifying images. But let's first take a regular neural network. A regular neural network has an input layer, hidden layers, and an output layer. The input layer accepts inputs in different forms, while the hidden layers perform calculations on these inputs. The output layer then delivers the outcome of the calculations and extractions. Each of these layers contain neurons that are connected to neurons in the previous layer, and each neuron has its own weight. This means you aren't making any assumptions about the data being fed into the network. Great usually, but not if you're working with images or language. Convolutional neural networks work differently, as they treat data as spatial. Instead of neurons being connected to every neuron in the previous layer, they are instead only connected to neurons close to it and all have the same weight. This simplification in the connections means the network upholds the spatial aspect of the dataset. It means your network doesn't think an eye is all over the image. The word convolutional refers to the filtering process that happens in this type of network. Think of it this way: an image is complex. A convolutional neural network simplifies it, so it can be better processed and understood. Let's look now at what's inside a convolutional neural network. Like a normal neural network, a convolutional neural network is made up of multiple layers. There are a couple of layers that make it unique: the convolutional layer and the pooling layer. However, like other neural networks, it will also have a ReLU, or rectified linear unit layer, and a fully connected layer. The ReLU layer acts as an activation function. ensuring non-linearity as the data moves through each layer in the network. Without it, the data being fed into each layer would lose the dimensionality that we want to maintain. The fully connected layer, meanwhile, allows you to perform classification on your dataset. The convolutional layer is the most important, so let's start there. It works by placing a filter over an array of image pixels. This then creates what's called a convolved feature map. It's a bit like looking at an image through a window, which allows you to see specific features you might not otherwise be able to see. Next, we have the pooling layer. This downsamples or reduces the sample size of a particular feature map. This also makes processing much faster, as it reduces the number of parameters the network needs to process. The output of this is a pooled feature map. There are two ways of doing this: max pooling, which takes the maximum input of a particular convolved feature, or average pooling, which simply takes the average. These steps amount to feature extraction, whereby the network builds up a picture of the image data according to its own mathematical rules. If you want to perform classification, you'll need to move into the fully connected layer. To do this, you'll need to flatten things out. Remember, a neural network with a more complex set of connections can only process linear data. There are a number of ways you can train a convolutional neural network. If you're working with unlabeled data, you can use unsupervised learning methods. One of the best popular ways of doing this is using autoencoders. This allows you to squeeze data in a space with low dimensions, performing calculations in the first part of the convolutional neural network. Once this is done, you'll then need to reconstruct with additional layers that upsample the data you have. Another option is to use generative adversarial networks, or GANs. With a GAN, you train two networks. The first gives you artificial data samples that should resemble data in the training set, while the second is a discriminative network. It should distinguish between the artificial and the true model. A lot of people seem to be asking what the difference is between a convolutional neural network and a recurrent network. It's actually quite simple. Whereas a convolutional neural network is a feed-forward network that filters spatial data, a recurrent neural network, as the name implies, feeds data back into itself. From this perspective, recurrent neural networks are better suited to sequential data. Think of it like this. A convolutional network is able to perceive patterns across space. A recurrent neural network can see them over time. If you want to get started with convolutional neural networks, Python and TensorFlow are great tools to begin with. It's worth exploring MNIST dataset too. This is a database of handwritten digits that you can use to get started with building your first convolutional neural network. If you want to learn more about convolutional neural networks, deep learning, and AI, visit PACT today.
Okay, and we can see in this video, the convolution network CNN is suitable for space and like a image, and the RNN is suitable for the time and the sequence. And if you want to know more CNN's details, you can see other professors' class, or you can check some books. And because we just tell the idea and the sort of CNN and didn't discuss the mathematics behind the CNN, because if you want to know the mathematics in CNN, you must know the sum, like array, and how to fill a number or empty area. Yeah, and this is for CNN's description. Then we will see the next. Next is the RNN for the time and the sequence. And neural network with memory and used in RNN. For example, we see the start filling. There is the ticket booking system, and somebody wants to travel Taipei on November 2nd. And the slot will fill this sentence and to pick up the keywords like the destination and the time of available. And from this sentence, we can pick up the destination is Taipei and the time of available is November 2nd, and this is the slot. Then, how this slot filling by the FIFO network, we can see the figure like this one. It input a word like this here, Taipei, and each element X will get the Taipei, and each word is the representative factor. Okay. And then we want our output is the probability distribute that input word belong to the slot. That means the slot need to correctly pick up the keywords like the destination Taipei and the time November 2nd, like this one. So here is the output. This is to destination and maybe is to time on available time or time for departure and so on. And then in the last slide, the sentence is I will arrive Taipei on November 2nd. Okay, and after this, it may think this arrival is not the keyword for destination or departure time or arrival time. So it will note this is not important or other words. And then Taipei will be the destination, not important, and this is time. And why is this sentence problem? This is only C will want to go to the destination and the time, but I don't know when will it departure or where the passenger comes. So in the ticket system, the AI or the computer cannot help the passenger to buy the ticket. And this is the sentence for leave Taipei on November 2nd, and this only has the place of departure and the time to leave. So how does the computer or AI knows? They will not find the verb like the arrive or leave to know it is attend to Taipei or leave Taipei. So if you didn't have memory, you will forget what verb it has. So in RNN, the output of hidden layer are stored in memory, like this one. They have memory. They have memory too, and the result or the sequence or the time or some words will store in the memory. And then when the hidden layer need the content, they will request to memory and pick up the words as another input. Okay, and let me take this again, like this arrive, and it will this word will dispatch to S1, and we'll get possibly the level in each slot, and the temporary words will store to the memory. And then the Taipei, this word will handled by the RNN, and then it will use this for another input, and then maybe see the Taipei is have some probability in some slot, and so on. And you can use this for any kind of words and to do the things. like store and so and list and so on. Then we will see the RNN will be like this one, like lift and Taipei, arrive Taipei, and their word will store it in the memory and to the next input. And this value stored in memory is different because one is left, one is the right. So the meaning of Taipei are different. Now we can see some detail or some example in this video. So we will see this video for no more detail about RNN. And again, in this class, we just tell the concept or the idea in neural network. If you really want to know the details of neural network and CNN, RNN, you need to join the class for a master or for a seminar, and then you can get the detailed algorithm and the detailed mathematical formula and the grammar in the class. Okay, and let me see this video for RNN.
What do you do if the patterns in your data change with time? In that case, your best bet is to use a recurrent neural network. This deep learning model has a simple structure with a built-in feedback loop, allowing it to act as a forecasting engine. Let's take a closer look. Recurrent neural networks, or RNNs, have a long history, but their recent popularity is mostly due to the works of Jürgen Schmidhuber, Sepp Hochreiter, and Alex Graves. Their applications are extremely versatile, ranging from speech recognition to driverless cars. All the nets we've seen up to this point have been feed-forward neural networks. In a feed-forward neural network, signals flow in only one direction from input to output, one layer at a time. In a recurrent net, the output of a layer is added to the next input and fed back into the same layer, which is typically the only layer in the entire network. You can think of this process as a passage through time. Shown here are 4 such time steps. At t equals 1, the net takes the output of time t equals 0 and sends it back into the net along with the next input. The net repeats this for t equals 2, t equals 3, and so on. Unlike feed-forward nets, a recurrent net can receive a sequence of values as input, and it can also produce a sequence of values as output. The ability to operate with sequences opens up these nets to a wide variety of applications. Here are a few examples. When the input is singular and the output is a sequence, a potential application is image captioning. A sequence of inputs with a single output can be used for document classification. When both the input and output are sequences, these nets can classify videos frame by frame. If a time delay is introduced, the net can statistically forecast the demand in supply chain planning. Have you ever used an RNN for one of these applications? If so, please comment and share your experiences. Like we've seen with previous deep learning models, by stacking RNNs on top of each other, you can form a net capable of more complex output than a single RNN working alone. Typically, an RNN is an extremely difficult net to train. Since these nets use backpropagation, we once again run into the problem of the vanishing gradient. Unfortunately, the vanishing gradient is exponentially worse for an RNN. The reason for this is that each time step is the equivalent of an entire layer in a feed-forward network. So training an RNN for 100 time steps is like training a 100-layer feed-forward net. This leads to exponentially small gradients and a decay of information through time. There are several ways to address this problem, the most popular of which is gating. Gating is a technique that helps the net decide when to forget the current input and when to remember it for future time steps. The most popular gating types today are GRU and LSTM. Besides gating, there are also a few other techniques like gradient clipping, steeper gates, and better optimizers. When it comes to training a recurrent net, GPUs are an obvious choice over an ordinary CPU. This was validated by a research team at Indico, which uses these nets on text processing tasks like sentiment analysis and helpfulness extraction. The team found that GPUs were able to train the nets 250 times faster. That's the difference between 1 day of training and over 8 months. So, under what circumstances would you use a recurrent net over a feed-forward net? We know that a feed-forward net outputs one value, which in many cases was a class or a prediction. A recurrent net is suited for time series data, where an output can be the next value in a sequence, or the next several values. So the answer depends on whether the application calls for classification, regression, or forecasting. In the next video, we'll take a look at a family of deep learning models known as the autoencoders.
Okay, if you have interest, you can see the other videos like this series of videos, and you can know more about the deep learning or other algorithm or other things. Okay. And in the last video, we see it talking about the LSTM, long short memory. That means in the sequence data more close to now, that it is important, and far from now information are less important, and this is supported or assumed by the LSTM. For example, if you have a number of passengers in the flight or in the taxi, and then you will know maybe this month the number of passengers can influence or can predict to the next month. But if you think 1 year ago or 10 years ago passengers number, and this is not have some important information to now. So in the long short-term memory LSTM, it will store the nearest information and will make the weight too high. That means the number of weight is higher or highest near right now, and the far information, the weight for the far information is very small. And here is the LSTM's figure. Because LSTM is belong to RNN, so it has a memory cell to store the information, especially for the nearest information. Then maybe this part is a part of network, so it input maybe from other part of network or from the input, and then it will input gate, and then the signal control to this gate or maybe this control is also from other part. Then it will output to the other part or to the output. It will depend on which part it is. Then it will go to the output gate, and also there is a signal control for the output gate. And here is the forget gate. When the information is the time or the sequence of information is far from null, it will return to the forget gate until this information is repeat again. Then it will pick up it to this memory cell. And this part we will call the LSTM. And the special network is 4 input and 1 output here. Okay. And I think this is a video here, but I will check it for the next class. And if this is a video, we will see it in the next class. Okay, and here is the introduce for the CNN, INN, LSTM. And then we will take 10 minutes break, and then we will see more example for the deep learning and know how influence or how efficient for the deep learning. Hope you like this course. Thank you.